Let's actually solve some systems of linear equations. And as we do this, let's take special care to keep track of the sorts of operations that we're doing, because what we're ultimately going to want to do is come up with a nice way of solving any system of linear equations, even if it's too big to picture what's going on, or even too big to do the calculations manually. So here's a 2 by 2 system. With this sort of 2 by 2 system, probably you're familiar with at least two different ways to solve this kind of system. So we could do substitution, but it turns out substitution is kind of clumsy for various reasons. So let's use the elimination or the addition trick for solving a system of equations. And so what I'd like to do is sort of add some decoration or some extra notation just to keep track of everything that we're doing. So with this with this particular system of equations, maybe the best thing to do to start out doing is, if you look at the first equation, every term in this equation has a factor of 3. So maybe it would be best to start out by multiplying the first equation by 1/3, just to get rid of that factor of 3. And to indicate that that's what we're doing, what I'm going to do is I'm just going to write, we're taking the first row, so I'm going to write R1, and we're multiplying it by 1/3, so I'm just going to write 1/3 R1. So this is just my way of indicating that we're replacing the first row with 1/3 times itself. So that gives us a new system of equations, and that's x plus 2y equals 3. And the second equation hasn't changed, so it's 2x minus y equals 4. Okay. And now the key thing here is that we have this kind of intuitive notion that this operation, replacing the first equation with 1/3 times itself, this operation shouldn't change the solutions of the system. So in fact, it doesn't even change it doesn't even change the solutions of the first equation. Right? Any solution to 3x plus 6y equals 9 will also be a solution to x plus 2y equals 3. Just to verify that, let's graph this thing. I'm going to use GeoGebra just because I have it handy. So we started out with the system 3x plus 6y equals 9 and 2x minus y equals 4. Okay. And, I made no special arrangement for this equation to describe parallel lines or anything, so as usual we get one solution at whatever this intersection point is. If we replace the first line with, you see GeoGebra has actually already simplified the first line, so it's already multiplied it by 1/3. So these two equations do genuinely describe the same collection of solutions. GeoGebra actually knows that. Okay, so the next step that we would take in solving this system of equations is, well, there are a couple ways to think about doing it. We could multiply the first equation by -2 and then add it to the second equation. How I'm going to write that is, we're going to take our second row, so that's R2, and we're going to add, or actually subtract, I guess, subtract 2 times the first row. So we're leaving the first row alone, so x plus 2y equals 3. But we're replacing the second equation with that equation minus twice the first equation. So 2x minus 2x is no x's, minus y minus 4y is going to be minus 5y. And then 4 minus 6 is minus 2. Okay, and this gives us another new system of linear equations. Now something a little bit strange has happened here because this the second equation from before and the second equation that we have now have different solutions. So, unlike after our first operation, these two equations do not have the same solutions. But our intuition or our experience is that doing this sort of operation, adding some multiple of one row to another row, it may change what the individual equations are, but it doesn't change the solution to the entire system. Let's check that that's happening on our graph. So let's replace equation 1 with, replace equation 2 with minus 5y equals minus 2. So I'm about to hit enter, but look at what happens to the intersection point when I hit enter. So the second line definitely changed. It's horizontal now, but the intersection point didn't change, right? So that's really verifying our idea that adding some multiple of one equation to another may change the individual equations, but it doesn't change the solution set. And that's good because we're looking for a solution to the original system. If we accidentally changed the solutions along the way, then we wouldn't be finding solutions to the original system anymore. Okay, so what would our next step be? Well, I guess now in this second equation, you see we have y all by itself. So our next operation would be to multiply this second row by minus 1/5, because that's going to get y by itself. So our first equation is still the same, so x plus 2y equals 3. And our second equation is now y equals 2/5. Okay. And, on the graph, you can see GeoGebra already multiplied the second equation by minus 1/5. And 0.4 is 2/5. So our graph is agreeing with our calculation so far. Okay, what would our next step be? Well, from here there's sort of two ways to go about it. Now that we know what y is, we could just take this first equation, plug in our y value, which is 2/5, and then finish solving for x. So x plus 4/5 equals 3, and then move the 4/5 to the other side. You get x equals, 3 is 15/5 minus 4/5 is 11/5, which is going to be 2 1/5. Okay, so that's one way to do it. But, as long as we're using these row operations, we could finish solving this system of equations just using row operations. So remember, one of the operations that we are allowing ourselves to do is add some multiple of one equation to another equation. So what we could do is take our first equation, or row 1, and we could subtract 2 times our second equation. Our second row. So 2 times our 2. You see, that's going to cancel this 2y term here. So this will give us x, and then right there are no x's in the second equation, and then 2y minus 2y, so no y's left, equals, and then 3 minus 2 times 2/5, that's 11/5, just like it was before. And then the second equation doesn't change. It's still y equals 2/5. Okay, so let's see what that looks like geometrically. So, what we did here is we just replaced x plus 2y equals 3 with the equation x equals 11/5. If we do that on our graph, so replace equation 1 with x equals 11/5, now keep your eye on the diagonal line that's labeled EQ1, and keep your eye on the intersection point. So when I hit enter, that first equation, the first line, it does change, but the intersection point doesn't change. So this process of doing these row operations to solve this system of equations, it does change the individual lines involved, but it doesn't change the collection of solutions. And that's really the key thing. So because these operations don't appear to change the solution set for this final system and the solution set for this beginning system are actually the same. but the solution set for our final system is clearly 11 over 5, comma 2 over 5, because look, it says that x is equal to 11 over 5 and y is equal to 2 over 5. So the process of solving a system of equations, a system of linear equations, is actually a process of replacing inconvenient lines with better and better lines, or nicer and nicer lines, until you get to a system where the solution is obvious. But the trick here is we can only do operations that don't change the solution set. So that's always the trick. And in this case, in this particular example, we did two kinds of operations. We multiplied by a constant, and we add a multiple of a row to another row. So those are the two operations that we allowed ourselves to do. And neither of these operations change the collection of solutions. So let's look at one more example. So this time we have a more complicated system, but we can still use the same operations and the same idea. So in our last example, we saw not only just operations we can use, but also a general idea for how to solve a system of equations. In fact, let me back up. So you see what we did here was we used this first term to zero out this the x term below it, and that left us with fewer variables. So let's use that idea and the same sort of operations to solve this system. So what we're going to do is we're going to use whatever x term is in this first equation to zero out the x's in the lower equations. That's a little inconvenient the way it stands because we have a 2x here. It would be nicer if we just had x, because then it would be easy to see what we should multiply, or all the arithmetic of adding a multiple of one equation to another would be much easier. But there's actually one more operation we can do on a system that we haven't done yet, and this operation doesn't change the solutions to this system, and it's just interchanging a couple of the equations. So let's just take row 1 and row 2 and just swap them. That definitely doesn't change these collection of solutions, because the collection of solutions only depends on the equations. It doesn't depend on what order you write the equations in. So switching the order won't affect the solutions. But it does give us an x in the very upper left, which is where we want it. So x plus 2y plus 5z equals minus 1. Our second equation is now 2x plus y plus 4z equals 4. And our final equation hasn't changed. It's minus x minus y plus 3z equals 5. Okay, so now the x term in our first equation is just 1 times x, which is kind of the nicest thing to have up here. So now we can start adding multiples of the first row to the other rows to zero out those x's. So let me do that here. So we're going to take row 2, and we're going to subtract 2 times row 1. At the same time, we could take row 3 and add row 1. Row 1 we aren't changing, so our first equation is still x plus 2y plus 5z equals minus 1. Now for row 2, remember we're going to subtract 2 times row 1, so 2x minus 2 times x is no x's, so there are no x's that show up in the second equation. And then y minus 2 times y, so that's y minus 4y, that's minus 3y. And then 4z minus 15z is minus 11z. And then 4 minus, we're not multiplying by 3, we're multiplying by 2. So 4 minus 10z is minus 6z. There we go. Okay, and then 4 minus 2 times minus 1, so that's 4 plus 2, that's 6. Okay, and then for row 3, we're going to take row 3 and add row 1. So minus x plus x is no x's, minus y plus 2y is y, 3z plus 5z is plus 8z. And then on the right-hand side, 5 minus 1 is 4. Okay, so at this point, notice that the first equation is the only equation that has x's anymore. And the second two equations, or the last two equations, I guess, have y's and z's, but no x's. So we can treat the last two equations as its own linear system. And this time it's a two-equation linear system in two variables. So we can now solve this smaller system of equations, right? So from now on, the first equation is going to stay the same, and we're just going to mess around with the last two equations. So first equation is going to be the same, x plus 2y plus 5z equals 1. And now, let's see, what should our move be here? Well, just like we used the first row to get rid of the x's below it, we should use the first row up here, or I guess it's the second row overall, but we should use this row, the first row with a y, to eliminate all the y's below it. But it would be nicest if there were a y times 1 right here, and there are a couple ways to make that happen. We could just interchange the second and third rows. So let's interchange row 2 and row 3. That's going to give us y, sorry, let me keep my variables aligned. Y plus 8z equals 4, and minus 3y minus 6z equals 6. We could also have divided the second equation by -3. That would have also worked. Okay, now we need to use our y right here to get rid of that 3y. So let's take row 3 and add 3 times row 2. So first equation isn't changing, so x plus 2y plus 5z equals 1. Second equation isn't changing, y plus 8z equals 4. And then third equation, we are adding 3 times the second equation. So minus 3y plus 3 times y is no y's left. And then negative 6z plus 3 times 8, so 3 times 8 is 24, minus 6 is 18. So plus 18z equals, and then 6 minus 3 times 4, 6 plus 3 times 4. 3 times 4 is 12, plus 6 is 18. Okay. All right. And now maybe as one last thing, we could take row 3 and multiply it by 1 over 18. So we get x plus 2y plus 5z equals 1, y plus 8z equals 4, and z equals 18. Now at this point, when we know what one of the variables is, now we can take that value for the variable, put it in the equation above. That'll let us solve for y, and then we can take our value for y and for z and put them into the first equation and solve for x. This process of, once you know one variable, rolling it back up to the previous variables, this is called back substitution. We could also continue to use row operations like we did in our last example, but back substitution, if what you really want is a solution to the system of equations, back substitution is usually a little easier. So taking our z and putting it into the second equation, we get y equals, I'm sorry, I wrote z as 18. It's not 18, it's 1. So put that into the second equation, you get y is 4 minus 8 times z, which is 1, so minus 8, so that's minus 4. And now that we know y and z, we can find x. So x is 1 minus 2 times y, so 2 times negative 4, minus 5 times z, and z is 1. And now we can just do the arithmetic here. So 1 plus 8 is 9, minus 5 is 4, I guess. Okay, so now we have a solution. X, y, z is 4 minus 4, 1. And I feel like when I cooked up this example, this is not what I was supposed to get. So it's possible I made an arithmetic error somewhere along the way, but you sort of get the idea, right? So in this example, we did two things that I want to point out. So the first was we noticed that there's one more row operation we can use that does not change the solutions to the system, and that is interchanging rows. And also, we sort of got a feel for how this might work, or how solving a system of equations using row operations might work in general. Right? We arrange to have a 1 in the upper left hand, or a 1 times a variable in the upper left hand corner, use that to zero out the stuff below it. And now you have a smaller system, so arrange to have a 1 in the upper left corner of that smaller system and use that to eliminate the variables below that. And then just keep doing that until you're down to a single variable, and then you can do back substitution. It kind of seems like this process should work for any system of linear equations, and indeed it does. If there is a solution to a system, this will find it.